So I said to you earlier today, I hopefully am not going to teach you anything new, but I'm going to cover some of the weird questions from the lesson 5 friction homework and just build on our understanding of friction, because it is a force that really dominates our life without us realizing. So look at example 1. It's a thought puzzle. Consider the bench below. You know what? How about those benches in the gym that you sometimes have to slide across to move them out of the way, those big wooden benches? How many of you have ever slid one of those or moved one of those? Most? Okay. So let's pick on Rachel. Rachel, you're sliding the bench across the gym at a constant speed. So Rachel is student number 1. Rachel has this meathead friend named Alicia. What Alicia's going to do while Rachel is sliding the bench, she's going to come along and she's going to sit on the bench. And I just saw a whole bunch of your eyes light up because clearly some of you have either done this or experienced this when one of your friends has done this. Okay, so all I'm saying is we're going to add an extra force down, and to put it into context, let's say Alicia's sitting on it. So student number 2 pushes down on the bench with force F. If you don't change how hard you push, if you maintain your constant applied force, what happens to A, the weight, B, the normal force, C, the friction, and D, the motion of the bench? You know what this is a good job for? Now, I did my initial free body diagram already. I think initially I had trouble getting the arrow lengths right. First of all, get the obvious one, everybody. Is it sinking into the ground like quicksand? Is it flying through like Superman? So initially, I think gravity and the normal force are the same length. You might want to make that downward pointing arrow just a tiny bit longer so it looks like it's the same length as the normal force, but it's up to you. And I think F applied and friction are the same size. How do I know? What's the 2-word phrase that tells me they must be the same size? Constant speed. Okay? All we're doing now is we're going to add an extra vertical force, whether it's Alicia sitting on it or whether it's just somebody pushing on it or an outside force pushing on it. We have an extra push down. Let's redo our free body diagram. What are the forces acting on it? Get the obvious one. So gravity is still the same. Is it sinking into the ground like quicksand? Is it flying through like Superman? Why would it be wrong to draw the normal force the same size as gravity in this situation? Kai, what? See, if I just do this, don't write that down, the vertical forces aren't balanced. This would have to be sinking into the ground like quicksand. Newton's first. Is it sinking into the ground like quicksand? So really what happens by pushing down on it, Alicia has increased the normal force. What if Alicia lifted up on it? What would happen to the normal force? It would get smaller. By the way, friction is what times what? Mu times the? If the normal force gets smaller, what happens to the force of friction? Gets smaller. It's why it's easier to slide something if you lift up. What if you lift it completely off the ground so it's not touching the surface at all? What's the normal force then? If it's not touching a surface at all, what's the normal force then? 0. Friction is what times what? So what's friction force then? And it's kind of Captain Obvious. Sarah's going, well, duh, Mr. Dewick, if you're not dragging it on the ground, if you lift it up, there's no friction. But I like that the math follows. No normal force? Yeah, of course, no friction. Here, though, what happened to the normal force when Alicia meanly sat on it? So what happens to the force of friction? Friction is what times what? So if normal force gets bigger? Yeah, 2 ways to make friction bigger. Number 1, change mu. When we saw that video of the snow trucks spreading gravel on the snow, that's what they were doing. Or increase the normal force. So friction will be larger. So for our answer, what happens to the weight of the bench? Remember, weight is mg. What happened to mg of the bench when Alicia sat on it? Nothing. Stayed the same. Ah, what happened to the normal force when Alicia sat on it? Got bigger. I'm lazy, so here is my abbrev. Fn increased. Up arrow to me is increased, down arrow to me is decreased. What happened to the force of friction? Well, if the normal force gets bigger, now remember, Rachel hasn't changed how hard she pushes. So in this second free body diagram, which way will this accelerate? Which way must it accelerate? Has to accelerate to the left. Which way was it moving? To the right. So it's going to slow down very rapidly, and then it's going to come to a stop. It's not going to keep going left. It's not going to spontaneously start accelerating left on its own. It's going to stop. And we'll explain why that's the case later too. So, slows, stops. It says explain your answer using principles of physics. I think we did with our free body diagram, and then we just used Newton's first, and our understanding of friction is mu times the normal force. So when does the normal force change, Donald? If there's an extra vertical force in the question. If you're pushing down, normal force gets bigger. If you're pushing up, normal force gets smaller. So we're going to generalize a tiny bit. Is it sinking into the ground like quicksand? No. Is it flying through like Superman? No. That does not mean normal force equals mg. Here's what it really means. All the forces down have to add up to all the forces up. Everything down equals everything. That's my short version. If it's not sinking into the ground like quicksand, it's not flying into the air like Superman, everything down has to equal everything up. That's another equation, and then I can get the normal force by itself if I need to. I'm going to be technical here, but I'm not going to test you on this. But I had a kid ask me this a few years ago, so I added this in the lesson. There is technically two types of mu's, two types of stickiness, of coefficients of friction. How many of you have ever noticed if you've been sliding something really heavy, or those benches in the gym, getting it moving requires a lot of force, but keeping it moving, you don't have to push so hard. How many of you noticed that? Okay. The reason is, technically, there's two types of friction. There's what's called static friction when it's at rest, and kinetic friction once it's moving. There's two types of mu's. Static mu and kinetic mu. Static mu is always a little bit bigger. Means you have to push harder to get it to start moving. Kinetic mu is a little bit smaller. Once you get it moving, you can ease up a tiny bit and it'll keep going. So there can be friction on an object even when it's at rest, since the hills and valleys will lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction, because static is not moving or changing. We're going to do a thought puzzle. We get to vote. So here's a question. Suppose Mr. Dewick pulls on a desk with a force of 2 newtons, and the desk does not move. Which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. And convince me. So here's what I'm talking about. Taking your desk again. Right now I'm pulling with about 2 newtons of force. This does not move. Which of those 4 statements is true? Once again, how high you hold your hand up is how sure you are of the answer. Okay? Who says, Dewick, it's obvious, it's not moving. A, static friction's got to be bigger. A. Oh, lots of you. Who says B? It's got to be B. Who says C? Who says D? Convince me. You can't hear in the back there. Kai is just berating himself because I think he's had an epiphany. What's an epiphany? A sudden realization when a bunch of dominoes fall into place and you suddenly go, aha. A classic epiphany in the movies is when Luke Skywalker finds out that Darth Vader is his father. The audience gasps, oh, Darth Vader. Vader is the German name for father. How did we miss that, by the way, if you didn't clue in on that? None of you? Huh? In German, I called my dad Vater, because the V sound is an F sound in German, but it's V-A-D-E-R. Lucas called him Darth Dad. Oh, sorry, Caden. Spoiler alert. Adam, if I say that you're correct, if the answer is B, it is B, convince me. Why must A be wrong? Kai, I heard you talking to yourself. Did you see why A must be wrong after you voted for A? Oh, why must A be wrong? If the forces aren't balanced, what must happen? So if it was greater, here's what would happen. We would live in a weird world where I would tug, and as soon as I let go, this would slingshot this way and knock them over. Would have to. Have I mentioned how powerful Newton's first law? Newton's first, very powerful if you really, believe it. It's gospel, but you got to believe it, okay? Trust it. It'll work. So it can't be A. And it can't be C or D, because the only situation where the forces are balanced. Now, here's why it's tricky. Static friction, it's a Newton's third law reactive force, which means it's only as big as it needs to be. Now I'm pulling with 4 newtons. You know how big friction is? 4. Now I'm pulling with 8.1 newtons. You know how big friction is? Now I'm pulling with 8.15. You know how big friction is? Now, suppose the biggest that this can exert a force of friction is 20 newtons. If I pull with 19, how big is friction? 19. If I pull with 19.9, I can actually feel through my hand this is just about ready to move. If I pull with 20.1, there. Friction can no longer match me. Having a disgusting moment, a thread has come loose in my mask. Ugh! It was in my mouth as I was talking. Ugh! Have to trim that off. Ugh! So static friction is this weird force in that it will always match what you're doing until it can't. If the biggest static friction can be is 50 newtons and you pull with 45, static friction will be 45. If you pull with 48, it'll be 48. 49.9, 49.9, but you'll almost be able to feel, yeah, it's about to move. 50.1, now you're going to have an acceleration in the direction that you're pulling. What was our answer? Why did we pick B? What was my argument? No. That doesn't explain why it didn't accelerate. Yeah? Wasn't Newton's third. Sadly, we'll have to write it out then. A equals 0, so forces are balanced. I live for the day when somebody just says, hey, Mr. Dewick, that's Newton's first. But I told you you didn't need to memorize which one was which, so that's fine. Okay. So static friction, that's what's acting when you have two objects that are at rest relative to each other. If you park a car on a hill, static friction is what's keeping the car from sliding down the hill because the car and the pavement are at rest relative to each other. Okay. A block of wood will remain stationary on a sloped table until you increase the angle. In other words, sorry for picking on you again. Get this thread out of the, okay, I got to cut this thread out because it's going to end up, I got this long thread right here. Ugh. Get thee away. That's better. So, water bottle. Stay away from that table. We'll go to this one again. Sorry for picking on you. if I go like this, are objects sliding down? There's enough static friction to hold them in place. Now, if I keep raising the angle, eventually static friction can't counteract gravity. They're going to start to slide. Sorry, it's out of that table. So, the force to overcome static friction is always a little bit bigger than the force needed to balance sliding friction. The force to get something sliding is always a little bit larger than the force required to keep it sliding. Sliding friction is called kinetic friction. What would be a good abbrev for kinetic? Okay, what would be a good abbrev for static? S. So you're going to start to see me use mu S and mu K. Having said that, I won't test you on this. This is just to explain why it is that it's harder to get an object to move than to keep it to move. We think it's because to overcome static friction, remember I told you friction was because of microscopic hills and valleys on the surface? We think it's because when they're at rest, those microscopic hills and valleys settle into each other. And so once you get it moving, they kind of skip over each other and don't settle into each other quite as much. We think. There's still doubt. Friction, by the way, to figure out what's going on at the subatomic level, it's really tough because to see things at that level is just really tough. So much of this seems to explain what's going on. So if I want it to be completely accurate, completely accurate, I would say something like this. A 5 kilogram object sits on a surface. Static friction, when it's at rest, has a coefficient of friction of 0.3. Kinetic friction, once it's moving, mu is only 0.25. A says determine the force required to move the object. You know what this is a good job for? I'm going to do my free body diagram in the white space right here. Right there. What are the forces acting on this object? Get the obvious one. What else? Yep. And it wants us to find the force required to move the object. So what we're going to do is we're going to do an applied force to the right. Is there friction in this question? So if we're pulling to the right, which way will static friction point? A says, determine the force required to move the object. Let's assume that we've pulled hard enough so that friction is just about to go, but we haven't quite started accelerating yet. Here's what I'm going to argue. I'm going to say, okay, the applied force equals static friction. As soon as I pull 0.01 newtons harder than that, we're going to accelerate. Friction is what times what? So F applied is going to be mu times the normal force. Which mu? Have we started sliding yet? So I'm going to use the static mu, the 0.3. Oh, I don't know the normal force. Oh, but look. Another force the same size as the normal force. Which one? So I get this. How hard do I need to pull just to get this thing moving? Mu static times mg. 0.3 times 5 times 9.8. Which is what? I can probably do this in my head. 5 times 9.8 is 49. 49 times 0.3, it's going to be 12 plus 2 points. 14.7? Okay. What if I pull with 14.6 newtons? What if I pull with 14.5 newtons? Okay. So, B. What if I pull with 10 newtons? So what will the acceleration be exactly as a number? How big is friction? Don't say 14.7. How big must friction be exactly as a number in your head? It's got to be 10. Do you know why? What's A? So forces must be. What if I pull with 12 newtons? Will it accelerate? What if I pull with 12 newtons? Will it accelerate? No. How big is friction? 12. Now, let's look at part C. What if I pull with 20 newtons? Will it accelerate? Okay, now I'm going to have to do an equation. Who's winning in part C then? F applied. Yes? Who's losing? Equals MA. First thing it wants me to do is it wants me to find the force of friction. Okay, I'm going to do that over here in the margin. Friction is mu times the normal force. In part C, are we sliding? So I'm not going to use mu static. I'm going to use mu kinetic. That's a lowercase k and an uppercase n. Or let's try that again. K, n. I don't know the normal force. Oh, but look. mg. So friction is going to be mu kinetic mg. When it was at rest, friction was 14.7 newtons. Once it's moving, it's going to be 0.25 times 5 times 9.8. I should be able to do that in my head. It's going to be 49 divided by 4. It's going to be 10 plus 9 divided by 4. 12.25? That's why once you get something moving, you don't have to push as hard to keep it moving. Friction kinetic is a little bit smaller than friction static. Kinetic friction is a little bit smaller than static friction. Let's walk that over here. What else did part C want me to find? Shay's theorem. How would I get the A by itself? So I'll have this. A equals F applied minus friction over M. In C, how hard are we pulling? What's F applied? 20? Minus, I know what friction is. Normally I do this all algebraically, but I just figured out friction. 12.25 divided by M is 5. I should be able to do this in my head. It's going to be 20 take away 12 is 8, take away 0.25 is 7.75. 7.75 divided by 5. What's a good trick to divide by 5? Divide by 10 and then multiply by 2. So it's going to be 0.775 times 2. 1.55? No, I'm wrong. What is it? 1.55? I should have trusted myself. So Donald, have I explained why once you start an object moving, it's easier to keep it moving? Having said that, we're going to pretend there's just one kind of friction for the rest of the course because I'm not going to be that fussy. So to keep the math nice, we're going to treat both types of friction as the same thing. So you can just remember that friction equals mu times the normal force, where mu is the coefficient of friction. Don't worry, Xavier, whether it's static or kinetic, I don't care. And the normal force is from what does FBD stand for? Free body diagram. You'll notice I haven't given you an equation on your sheet for the normal force. There isn't one. Speaking of normal force, let's muck around with the normal force. If you look at example 4, you might notice that several of the pictures, B and C, have extra vertical forces. So example 4 says find the maximum force of friction between the mass and the ground for the following objects. Technically what we're finding is mu static friction, but we're going to pretend there's just one. Okay. Well, for all of these, friction equals mu times the normal force. What's mu in A and B and C? 0.35? Yes? Okay. We need to figure out the normal force. How will I do that? This is a job for a? Okay. What are the forces in A? Get the obvious one. What else? Is it sinking into the ground like quicksand? Is it flying like Superman? Then everything down has to equal everything. So in this case, the normal force, I think, equals mg. If you want me to calculate the force of friction for A, it's going to be mu times the normal force. I always start there. But Hannah, I'm going to argue in this case the normal force is mg. It's going to be 0.35 times 8 times 9.8. Which is what? Sorry? 27.4? Even? Let's for this one, I'm going to carry the extra sig figs for a reason. 27.44 newtons. Okay. I like B and C, I like B and C, I like B and C. Here's what I mean. On your test, I'm going to give you one question, maybe two, where there's extra vertical forces. Can you see the extra vertical force? Somebody is pushing down with an extra 55 newtons. This is still a job for a. What are the forces acting on this? Get the obvious one. Is it sinking into the ground like quicksand? Is it flying to like Superman? Then everything down has to equal everything up. Here, is the normal force going to be bigger, smaller, or the same size as mg? I'm going to tell you right now, is there an extra vertical force? Not the same size. So is the normal force going to be bigger or smaller? Is the ground having to push back harder or less hard? Normal force is going to be bigger. In fact, everything down will equal everything. I'm going to say that again. Everything down will equal everything. I'm going to write that as an equation. Everything down, mg and plus 55, will equal everything up. You know what normal force is, Hannah? mg plus 55. Has to be. That's not what they wanted me to find. They wanted me to find friction. So let's start out again. Friction is mu times the normal force. I don't know the normal force, and I can't really say, oh, but look. But wait a minute. I have an expression for the normal force. What can I replace the normal force with? mg plus 55. Wherever I see the normal force, what can I write instead? mg plus 55. What can I substitute into this equation with brackets? It's going to be mu bracket mg plus 55, close bracket, because it's mu times the whole normal force. Friction is going to be 0.35 bracket 8 times 9.8 plus 55. Friction will be more in B. What do you get? What do you get? Sorry? 46.7 even? 46.69? This is my way of saying figure out how brackets work on your calculator, because if you didn't get that, I'll help you, but figure it out. Try this. What about C? It wants me to find friction, so I'm still going to go friction equals mu times the normal force. I'm going to have to figure out the normal force. What are the forces acting on this object? Get the obvious one. Here, oh, is it sinking into the ground like quicksand? Is it flying like Superman? Everything down is going to equal everything up. Here, is the normal force going to be bigger, smaller, or the same? So wait a minute, there's an extra vertical force. That's not the normal force. Someone's pulling up. Normal force is not going to be the same size. So normal force is going to be bigger or smaller than mg. Someone said bigger, someone said smaller. The good news, one of them's right. The bad news, one of them's wrong. Smaller? How come? 55 newtons worth of gravity is being canceled out by somebody. The ground doesn't have to cancel that part out. I'm going to exaggerate it. Yep. Do a little tiny normal force to let myself know it's smaller. How will I figure out this normal force? Are we sinking into the ground? Are we flying through the air? Then everything down, mg, equals everything up, normal force and that 55. Garrett, how would I get the Fn by itself? You're saying the normal force is mg minus 55? And that's what's going to go in here? I agree with you. It's going to end up being 0.35 mu bracket 8 times 9.8 minus 55. Which is what? $8.19. Anybody else? Yeah. So, to get A accelerating to the right, you would need to pull with more than how many newtons? 27.44. You would need to pull harder than what to get B accelerating to the right? 46.69. And you would have to pull harder or push harder than how much to get 8.19? Okay. Put your pencils down, look up. For each of the blocks below, it says, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? I'm going to draw a little line right down the middle of the page here. And we're going to actually do these kind of at the same time. We'll do A for both of them, B for both of them, C for both of them, D for both of them, because I want you to notice where they're the same and where they're different. What's the difference between the two diagrams? In the diagram on the right, what? Eduardo, you're right. What? Yes, an extra 15 newtons down. Will that make the normal force bigger, smaller, or the same size on the right-hand side? Okay. It says find a vertical force equation. No. I'm not even going to do that first. You know what I'm really going to do first? What might this be a good job for, Adam? So Adam, you and I are going to do this left-hand side together, okay? What are the forces acting on this left-hand block? Get the obvious one. Good. What else? Bigger, smaller, or the same size as mg? Are there any extra vertical forces? Same size. What else? There's that 20 that's coming from off the page. What's the name that we've given to the mystery force that's coming from off the page that I don't want to make up a story about? We call that F applied. So I'm going to draw an arrow there, and I'm going to put next to the 20 and equals F appap, just so I don't miss it. Is there friction in this question, Adam? How do I know? Because in the diagram, they stuck a little mu there. See it? And I think that's for the whole surface for both pictures. Which way would friction point if I'm pulling to the right? Good. Good. Ethan, you and I are going to do the right-hand diagram together. What are the forces acting on the right-hand side? Get the obvious one. I totally agree with you. What else? Bigger, smaller, or the same size as mg? Bigger. In fact, if I was really fussy, it would be the same length as however long you drew mg plus that 15. That's how long we should draw up, except I tend to exaggerate it so it catches my eye, so I know, normal force is different this time. Ding, 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 ding. What else? What did I call that 20 Newton force? Yep. Is there friction? Yeah. Okay. Good. Part A. Part A. Adam, part A says, write a vertical force equation. Are we sinking to the ground like quicksand? Are we flying each other like Superman? Then everything down equals everything up. What's everything down in my free body diagram? There's only one arrow pointing down. Don't overcomplicate it. mg equals everything up. What's the only arrow pointing up? There's my vertical force equation. Ethan, for the right-hand diagram, am I sinking to the ground like quicksand? Am I flying to like Superman? Then everything down has to equal everything up. What's everything down? There's two things. There's two things. There's another arrow pointing down. Force applied is not pointing down. Just read me the number that's pointing down. Thank you. Has to equal everything up. Yep. I guess in this case, the normal force is mg plus 15. If that 15 was pointing up, I would have mg equals normal force plus 15, and then I would minus the 15 over to get the normal force by itself. And this is why I said to you, I'll never give you an equation to find the normal force. You'll have to just derive it from the free body diagram. Okay. Adam, what does B want me to find? Sorry? Force of friction. Friction equals what times what? Everyone. Mu times the. Let's write that down. What's mu? I don't know. What's mu with you? Oh, 0.12. I don't know the normal. Wait a minute. I do know the normal force. What did you write in part A? The normal force is equal to? Well, that's easy. So friction in part B is going to be 0.12 times 10 times 9.8. I can do that in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 11.76. Yes? 4 sig figs in my head, just saying. By the way, I would take 11.8. I'm only going to 4 sig figs for the mental brag that I did it in my head to 4 sig figs. So full disclosure here. Oh, Ethan, let's do B on the right-hand side. What does it want us to find? Friction. Friction is what times what? I don't know the normal force. Oh, yes I do. The normal force is equal to, in brackets, mg plus 15. It's going to end up being mu bracket mg plus 15. That's the normal force. Don't think mu mg and then add 15. It's mg plus 15, then times mu. That's the order we got to do it in. So it's going to be mu 0.12. Do this one in your head, Mr. Dewick. Well, maybe. Times 9 point. Sure, I can. 10 times 9.8 is 98 plus 15 is 113. 113 times 0.12. Ooh, I can do that. 113 times 0.12 is going to be 113 times 0.1, 11.3. So it's going to be 11.3 plus 2.26, 13.56. Adam, part C says write a horizontal force equation. I've scrolled down, but you have it in front of you. Which way do you think your mass is sliding? Who's winning? Who's losing? Equals? Yep. What does winner minus loser always equal? MA. Ethan, look at your mass. Which way do you think it's sliding? Who's winning? Who's losing? Equals. And you'll notice it's kind of weird. We got identical force equations for both situations. That's because all that's changing actually is the normal force, which is changing friction. But the tug of war, it's still between the same two forces. The numbers will be different, but it's still the same tug of war going on. What does D want me to find, Adam? Oh, Shay's theorem. Yes, get the A by itself. A is going to be F applied minus friction all over M. All right. Adam, how big was F applied? I think the question told you, I hope. 20. How big was friction? We actually calculated it. 11.76 divided by, what was the mass? 10? I can do that in my head. 20 take away 11 is 9, take away 0.7 is 8.3, take away 8.24, 0.824? Double check me. Yeah? That's just dividing by 10. That's not too impressive. Ethan, what did D want me to find? Oh, Shay's theorem. And again, you'll notice I even get the same acceleration equation as part C. What's going to change? The friction force. Why? Because the normal force is not mg this time. Adam, what was F? Ethan, what was F applied? Friction was 13.56 divided by 10. Ethan, what's 20 take away 13 in your head? 7. What's 7 take away 0.5? 6.5. Take away the 0.0. 6.44. You know what 6.44 divided by 10 is? 0.644. I'll bet you. Is that right? Oh, Ethan, I was going to walk you through it, and you were going to get the little nerdy adrenaline rush of doing math in your head, but couldn't get you there. Turn the page. You don't need to memorize any of these, but since I've talked to you about mu, the coefficient of friction, here are just some common ones. So wood on wood is about 0.25. Steel on steel is terrible. It's 0.5. So how do we get around that with machinery? You lubricate it, yeah. When we lubricate it, the next one goes down to about 0.1. It gets much slipperier. Rubber on dry asphalt. This one anywhere from 0.4 to 0.75. It varies. You may have noticed on hot summer days, pavement is way stickier than on cold winter days. So there's a fair bit of variation there. But what I do want you to notice is when it's raining, what happens to your coefficient of friction? That means it's going to take you about twice as far to stop when it's raining. Slow down, please. Has nothing to do with your skill. I'm a good driver. I can drive in the rain just fine. Has nothing to do with your skill. Sarah, you cannot argue with the physics. You have a smaller coefficient of friction, so friction is smaller. If you actually run the equation, you'll find, oh, it's going to take me twice as far to stop. Slow down. Rubber on ice, steel on ice. You'll notice rubber on ice is really bad. That's why walking on ice in sneakers is tougher than skating on ice, right? Can you have a coefficient of friction bigger than 1? Yes. Rubber on glass has a coefficient of friction of around 2 approximately. Try sliding a piece of rubber along a window and that does not want to slide at all. It can, but you got to work at it. That's why typically you can stick a piece of rubber on the window and it'll just stay there. It'll counteract gravity. A dragster has tires with mu's of 2.8. Dragster tire has a coefficient of friction of 2.8. Shouldn't a tire with so much friction slow the dragster down? Using principles of physics, explain why a high coefficient of friction is essential for racing. Hint. Draw a... Why would you want a high coefficient of friction? Let's draw a free body diagram. Here's the dragster. Braden, what are the forces acting on the dragster? Get the obvious one. Gravity. I agree. What else? Go systematically. Is it sinking into the ground like quicksand? So, normal force. Let's pretend this dragster is accelerating to the right. So which way must there be an unbalanced force pointing? What force? Nope. What? Yeah, friction's what makes car go forward. Can you see, Allie, why that explains why you would want tires with a high coefficient of friction? Since friction is mu times the normal force. And by the way, there's something else. If you've ever seen a dragster, which are the tires that actually generate the friction? The front tires or the back tires? The rear tires. The front tires are just along for the ride. They just spin freely. Friction is what times what? Mu times the... What's the normal force equal to in this picture? Where is most of the mass located in a dragster? Over the front tires or over the back tires? We've thought of that too. Bigger normal force over the rear tires. Absolutely. Okay? Yeah. Braden, have I convinced you okay? Yep. So, bigger... You can write the mu symbol. I don't know how to type that. Bigger F friction, bigger acceleration. Because if F equals ma, it's not like the mass of the dragster gets bigger. You'll get a bigger acceleration with a bigger force. Dragster tires are also very, very expensive. Typically, you can only use them once or twice, and then they're shot. Anybody here do drag racing? I should have asked. Nobody into racing? Okay. Example 7. I think, is it 2 more and we're done? 3 more and we're done. There we go. Okay. I know I've been talking a long time. A force of 120 newtons is needed to push a box along a level road at a steady speed. Ding, 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 ding. If the force of gravity on the box is 250 newtons, what's the force of friction between the box and the road? What's the coefficient of kinetic friction between the box and the road? Okay. I think there's something I would do before I even start this question. Any guesses? Adam. I think now how do I know to do a free body diagram here? First of all, it doesn't say net force, which means I could go straight to F equals ma. I see a force here. I see friction, I see gravity. I see the force of friction. Sarah, is there more than one force in this question? That's when I probably want to do a free body diagram. Right there. What are the forces acting on this box? Get the obvious one. What else, Eduardo? Bigger, smaller, or the same? Oh, by the way, look. I can even tell you how big gravity is. It told me it's 250 newtons. I'll stick that on there just for giggles, to remind myself, hey, I know it. Also to remind myself, don't multiply that by 9.8. That's not the mass. What else? Same size as gravity or bigger or smaller? Do you see any other vertical forces mentioned in this question? Then I can even say Fn equals 250 newtons. Yay! What else? It says the force of 120 newtons is needed to push this box along a level road. What do we call an outside force like that? This is F applied. And apparently that's 120 newtons. What else? Tell me when to stop drawing friction. Let's try that again. Tell me when to stop drawing friction. How do I know to make it the same size as F applied? Steady speed. A is 0. Okay. That's also 120. Oh, you know what? I just answered A. A said, what is the force of friction? I was all set to go, no, it's sitting there, 120. Cool. Mason, what's B want me to find? Sorry? Keep reading. Of? Coefficient of friction. Hey, what's mu? I don't know. What's mu with you? Wants me to find mu. Okay. What's the equation? What's the only equation that has the mu in it? Friction equals. Good. How would I get the mu by itself? So I guess mu is going to be friction divided by F. Oh, I know friction, 120. I don't know the normal. Oh, yes, I do. It's the same size as mg, which is 250. Well, that turned out to be a lot less painful than I expected. That's going to be 12 divided by 25. That's the same as, is it 0.48? Units for mu. Is that a force? No. What are the units for the coefficient of friction? And in fact, you can see, Hannah, it would be newtons divided by newtons. All your units would cancel. Nothing. Cool. Turn the page. A dragster's tire is accelerated from rest, I would probably mentally or actually underline from rest, to a speed of 48, blah, 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 blah. Okay. What's A want me to find? I wrote A equals question mark and not a free body diagram because as I read this, I saw from rest and a 48 and a 64. I think I'm in pre-Christmas. I'm looking for an equation. Well, let's see. VI is 0, VF 48, D 64. Which equation? Squared. Thank you. That forgetting the squareds is more common than you realize. A couple of you did that on the test. We'll go through the test in a couple of days. It's going to be 48 squared minus 0 squared all over 2 times 64. Do that one in your head, Mr. Dewey? Well, maybe. 48 squared, that's 6 squared times 8 squared. So the 8 squared, so it's 6 squared. 18? Yeah. Almost 2 G's. Just shy of 2 G's. Okay. Yeah, that's about it. Dragster acceleration. B. B. Shay, what's B want me to find? The what force? The what force? F equals ma. And double check, but I did on your green sheet, I wrote F net equals MA as the formula on your green sheet, did I not? That's what I'm saying. It says F net, MA. No need to go winner minus, I've done that already. So what was the mass? 540 times 18, which is what? Sorry? 9720? Anybody else? C. Sarah, what does C want me to find? Now, my first thought would be friction is what times what? Mu times the... What does D want me to find? So I can't do that. How can I find friction? Adam, you know what this might be a good job for? Let's try doing a little free body diagram. I got, the way I've set it up, I've got some white space over here, so I think I'm going to do my free body diagram right here. What are the forces acting on this dragster? Get the obvious one. What else? What else? Which way is it accelerating? So definitely has to be an unbalanced force pointing that way. What makes a dragster accelerate? Don't say F applied. What? Oh. Is there a force pointing backwards? Technically, if we were being really fussy, Mason, air resistance, although do dragsters have much air resistance, or are they pretty aerodynamic? Now you're understanding why they're shaped all the same, right? Okay. Who's winning? Who's losing? It's like elementary school sports day. No losers. So friction equals... Oh, by the way, in part B, didn't I just find MA? Friction is going to be 9,720 newtons, apparently. Question, Naomi, or not?
Oh, no.
Okay. So I'm doing this question just to remind you, Mason, don't be mechanical. Oh, friction, mu times normal force. Okay, if you don't have mu, we got lots of options still. Oh, Sarah, what did you say D was asking us to find? What did I find in part C? Friction? Oh, friction is mu Fn. How would I get the mu by itself? Mu equals friction divided by Fn. So it's going to be, oh, I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. What? Folks, I'm feeling lazy. I don't want to rewrite this. Look up. I'm going to cross out the Fn and just put a little mg right there instead. If you do that in your homework, I'm fine with that. So it's going to be 9,720 divided by 540 times 9.8, which is what? You get 1.84? And I got nervous at first because it was a big mu, bigger than 1, but then oh, wait a minute, dragster tires. We said those are sticky on purpose. Is it 1.84? No units. Okay. So in the previous question, we found the mu when A was 0. Here we found the mu when there was an A. I didn't have a loser, but could I handle it if there was a loser too? I think so. You'd still divide by the normal force. You would just have winner minus loser over the normal force. Okay. Get friction by itself. Oh. This is as tough a question. Is this the last question? This is as difficult a question as I can throw at you. Look at the picture. Is there an extra vertical force? Yeah. So is the normal force equal to mg? Nuh-uh. Look at the picture. Is there an applied force, an outside force? Yeah. Oh, and what am I asking you to find? Mu. Are we at a steady speed? Is A 0? This is as tough as I can throw at you. Any suggestions on how we might want to start? Before that, I think free body, although did they give me a picture? I'm going to wimp out and just label the picture. In the previous couple, I hadn't given you a picture at all, so I represented the mass as a dot and did the whole one. Here, they gave me a picture. Okay, Kai, what are the forces acting on this? Get the obvious one.
Gravity.
Good. What else? Is the normal force going to be bigger, smaller, or the same size? Wait a minute, there's an extra vertical force, so not same size. Is the normal force going to be bigger or smaller than mg? Smaller? So I'm going to really exaggerate it. Yoink. Cool. What else? Before that, there's one that's sitting on my diagram that I see staring at me. Be obvious here. There's an F applied. I usually draw an arrow on there just to remind myself, hello, I saw it. And what else? Friction. Mr. Dewick? Yes, Kai? What if friction was winning and I didn't know it? In other words, what if this wasn't speeding up? What if it was? How would I find that out? You would end up getting a negative acceleration on your calculator if you were solving for A. And then you would say, oh, pick the wrong winner. It's pretty easy to change the question, though. You kind of erase a couple of arrows. Often on your calculator, you can just backspace and change minuses to plus and pluses to minus and resolve the question. So it's not that big a deal. Here, I mean, they told me it's accelerating to the right, so I agree with you. Who's winning? Who's losing? What's that going to equal? What's this question want me to find? Where's mu hidden inside of? Let's get friction by itself. What's right in front of friction that I don't like? The negative. Oh, swappy dance. I'm going to get F applied minus MA equals friction. What am I trying to find? Mu. Where's mu hidden inside of? So my next step is going to be to replace friction with what times what? Okay. How would I get the mu by itself? Boom. Boom. Do I know F applied? 125. Do I know M? Yep, 20. Do I know A? They told me. I don't know the normal force. And I can't say, oh, but look. I'm going to have to do a little bit of math over here. I'm going to have to write a vertical force equation. Are we sinking into the ground like quicksand? No. Are we flying here like Superman? No. What that really means is everything down equals everything. Kai, give me a vertical equation. Everything down. Everything down equals everything up plus 85. How would I get the Fn by itself? So you're telling me that Fn is going to be mg minus 85? And you're saying that's what I can stick down there? So I'm going to have this. Mu is going to be F applied minus MA all over mg minus 85. I'll definitely have to have brackets around the top. Definitely have to have brackets around the bottom. Let's plug in our numbers. What was F applied, Kai? 125? Minus what was M? And A? All over 20 times 9.8 minus 85.
Do this one on your head, Mr. Do It.
Yeah, this is about my limit. Sorry. I don't know. Let me type it. Do you get 0.549? Oh, do you get 0.549? 0.549 repeating? Okay. So 0.550, I guess, if I round off properly. How slippery is that? Sticky-ish. Kind of tires on pavement-ish. Okay. And here's my hope. I hope today you didn't learn a thing. I hope there was nothing new today. It was just, let's see what we can do with this. What's your homework? Number 1. Number 2 is good. Number 3 is good. Number 3 is so easy that it's tough. Your hint is draw a free body diagram on the race car. Four is good. You know what? 4 and 5 are the same, so I'll just give 4. 6 is good. 7 is good. 8 is good. 9 and 10. 7, 8, 9, and 10, that's about as tough as I'm going to ask you on your test. And I'm not going to put 10 of these on your test, 1 of them. And what I mean by that is I'll give you one question where there's a normal force that isn't equal to mg, and I'll either give you mu and say find A, or I'll give you A and say find mu. The rest of the class is yours. Thank you very much for your patience, my angels.